one thing you need to do to prepare for that exam is prepare an equation sheet that you can refer to during the exam. So a good place, a good source for getting the equations to write down on your equation sheet is the exam study guide at the end of every chapter. This exam will cover 4 chapters. I guess it's chapters 27 to 31. No, 28, 29, 30, 31. Here's the exam study guide from chapter 31. Chapter 31 is the chapter on electromagnetic waves. It's on page 965 of the textbook. And you see it has 12 little boxes where it has information from the chapter. And in each box, there are one or maybe a few equations. And you should know those equations. So I would say a good way to prepare for the exam is to review the exam study guide in each chapter and copy down the equations. Make sure you understand the equations. It's not enough to just have the equation written down. You have to know what it means. Make sure you understand it. And write that down on your equation sheet. And that will pretty much ensure that you have all the equations that you need to answer the questions on the exam. So I want to go over some of the problems from the assignment for this week on electromagnetic waves, and we'll see how these equations can be used in each of the homework problems. And so if you know how to use these equations in the homework problems, you'll also know how to use the equations when it comes to the exam. So, chapter 31, there's a section on the displacement current. That was Maxwell's invention or hypothesis that he needed to complete his field theory. You can read about that in the book, or you can watch about it on the screencast at the YouTube channel. The displacement current is epsilon zero, that electronic constant, times the rate of change of the electric flux. And we refer to that as a current, or Maxwell called it a current, because it appears in Maxwell's equations in exactly the same way as the particle current. So Ampere's law says that the circulation of the magnetic field around a closed loop is equal to mu zero, that's just the universal constant, times the current enclosed by the loop, plus, this part Ampere didn't know, but Maxwell determined it had to be included, the displacement current going through the surface bounded by the loop. Now you see the similarity of that equation to Faraday's law. Here's Faraday's law. And then here are the Gauss's law equations for electricity and magnetism. So these are Maxwell's field equations. And again, there's a section of this in the textbook, or you can watch the screencast on the YouTube channel and find about how Maxwell came up with this theory around in the 1860s. So, 150 years ago or so. And of course, we still use the same equations today. So these equations have certainly stood the test of time. And Maxwell proved or realized that if you have no charge and no charge current, these equations can be solved by waves. So in vacuum, in a region where there is no matter, there are no charged particles, there are no charged currents, there are effects, electromagnetic effects in the form of waves. And this is the form of a plane wave. This is an example in which the electric field oscillates in the Y direction, the magnetic field oscillates in the Z direction. They both have harmonic space and time dependence with parameters k and omega. K here is 2 pi over the wavelength. Omega is 2 pi times the frequency. The field equations require, in an electromagnetic wave, the electric field is C times the magnetic field. This implies that the electric field energy density and the magnetic field energy density are in fact equal. Of course, E can't be equal to B because they don't have the same units. E is equal to C times B, where C is the speed of light in vacuum. And again, Maxwell showed that the solution for the wave equation, C is 1 over the square root of mu 0 epsilon 0. So he related those electric and magnetic constants to the speed of the electromagnetic waves. And he recognized that the answer was equal to the speed of light. And that's how Maxwell determined that light is an electromagnetic wave. And all other frequencies, besides just visible light, can also form electromagnetic waves. So there's an infinite spectrum. Now here's some of the properties of electromagnetic waves. Power flow. Electromagnetic waves carry energy. So if we have a wave, let's say it's traveling in this direction, it's moving energy in that direction. If you set up a little area, let's say a little area delta A, the rate at which energy passes through that area, delta P over delta A, that's the power per unit area. That's also called the Poynting vector, S, is E squared over C times mu 0. That's one of the equations from the exam study guide. The intensity of light, or the intensity of any kind of electromagnetic radiation, is defined as the average of the Poynting vector. You know, E is oscillating in time. E oscillates between the amplitude and plus and minus the amplitude. E squared oscillates between 0 and the amplitude squared. The average value of the power flow will be 1/2 E squared divided by C mu 0. And 1/2 E squared is the root mean square value of E. So this is the equation which is given in the study guide, and you might have to use that equation for one of the homework problems. There's a discussion of the energy densities. The electric energy density is 1/2 epsilon 0 E squared. The magnetic energy density is 1 over 2 mu 0 B squared. Those are the results. Those are results that we had from earlier in the semester. And now, because of this relation, E is equal to CB, and also C is 1 over mu 0 epsilon 0, that means the energy density in the electric field is equal to the energy density in the magnetic field. So an electromagnetic wave has both electricity and magnetism. You can't separate them. They have to be both present in equal amounts in terms of energy. There's a section on radiation pressure. We'll look at an example a little later which has radiation pressure. Radiation pressure is the pressure exerted by light when it hits a surface. Not necessarily just visible light, any kind of electromagnetic wave. But in particular, when visible light hits a surface, it exerts a pressure. How big is the pressure? How large is the pressure? Well, it's the intensity over the speed of light. That's if the surface absorbs all the momentum. So a black surface. But on the other hand, if the surface reflects all the momentum, then the pressure is twice as large. It's 2 times the intensity divided by the speed of light for a shiny surface. Now, there also is a discussion in this chapter of polarized waves, and I don't have anything much to say about polarized waves tonight, but I think there are some homework problems about polarized waves. And again, some of the equations are written down in the exam study guide. But these are the kind of equations you need to have on your equation sheet, and you need to know what they mean and how to use them. So now in the homework assignment, we're going to see how to use some of these things. So we'll go over several of the homework problems. Here's a problem on displacement current. You have a capacitor in the form of a parallel plate capacitor. You have 2 plates, current I0 coming into one side, current I0 going away from the other side. The distance between the 2 plates is D. The area of the plates is A. And the question is to calculate the displacement current density. Now, current density means current per unit area. So we have a certain amount of electric current coming in, a certain amount of electric current going out. We want here the displacement current density. So we want for I epsilon naught d phi dt. That's the displacement current. Then divide by A, that gives us the displacement current density. Now, this flux phi is the electric field times the area. So you see, when I divide out the area will cancel out. The displacement current density, it's actually a vector. It's in the direction of the motion of the change in flux. It's epsilon 0 dex dt, because the 1 over A cancels the A. So that's displacement current density. That's what we're trying to calculate. Now we have to know the electric field between the 2 plates of a capacitor. Well, you remember the relation between electric field and potential, the electric potential. The electric field is the rate of change of the potential. If you really want to be accurate about it, it's the negative rate of change of potential. But we're not so interested in the sign here. So we'll just say it's the rate of change of potential with respect to the distance. It's dV dx. And now the change in potential between the 2 plates, let's call that delta V. And the distance between the 2 plates is D. So dV dx is delta V over D. And now the change in potential between the 2 plates is the charge separation. So one side will be positively charged, let's say Q, and the other side will be negatively charged, say minus Q. Q divided by the capacitance is the difference in the potential between the 2 plates. So we studied capacitance earlier in the semester. Delta V is Q over C. No, it's Q. Well, what's C? Well, C, the capacitance for a parallel plate capacitor, is epsilon naught A over D. That was from an earlier chapter. But now what's Q? Well, Q will depend on the current. You're delivering charge onto the left-hand plate. You're taking charge away from the right-hand plate. That is to say, you're putting positive charge onto the left-hand plate. You're taking positive charge away, leaving negative charge on the right-hand plate. And the rate of change of the charge is equal to the current, I0. The charge current. In the wire here, this is a wire which is connected to the plate. So EX is Q over C times D. C times D is epsilon naught A. dEx dt is 1 over epsilon naught A dQ dt. And dQ dt is the current. So we do have a changing electric field here because the charge is changing on the two plates. So as we're accumulating more and more charge on the left plate and taking positive charge away from the right-hand plate, the electric field between the plates is increasing. So there's a rate of change of charge. And that's what gives you displacement current. So in fact, dq dt is equal to the charge. Charge is amps, that's coulombs per second. So the displacement current is the displacement current is A times dE dt. dE dt is epsilon naught. Sorry. This is the displacement current. So that's the current density, epsilon naught dE dt times A. You see the A's cancel. I guess I said that earlier. Well, actually, the epsilon naughts cancel. So in fact, the displacement current between the plates is just exactly the same as the charge current coming into the left plate. That's kind of the way, that's one of the ways that Maxwell saw that for consistency, there had to be something playing the role of current where there's a change of electric field. And of course, the problem is to calculate the displacement current. So that's I0, which is given in the problem, divided by I, which would be divided by A, which is also given in the problem. So that's an example of displacement current. That doesn't involve a wave, but of course, displacement current is necessary in order to have waves. Now let's look at a problem which does involve a plane wave. You have a plane wave where the amplitude of the electric field is alpha. What's the amplitude of the magnetic field? Well, if you go back to the equation sheet that you've prepared, E is C times B. So the amplitude of E would just be C times the amplitude of B. They have the same X and T dependence. If I multiply C times B, I just get E max is C times B max. So that just comes directly from the equations on the exam study guide. So E is alpha, B is alpha divided by C. So here's the electric field. That's oscillating one direction. The magnetic field is oscillating in a perpendicular direction. The wave is propagating in the third direction. The direction of oscillation of the electric field, the direction of oscillation of the magnetic field, and the direction of propagation of the wave form an orthogonal triad. They're all perpendicular to each other. And amplitude means the maximum value of E, where the E takes its maximum value is at the crest of the wave. The crest of the magnetic wave occurs at the same points because E goes like sine kx minus omega t. B also goes like sine kx minus omega t. They have the same X and T dependence. So the point where at a particular time, the electric field is at its crest, the magnetic field is also at its crest, and alpha is C times B. So that's an easy one. Suppose a cell phone has an antenna with length L. What's the signal frequency if the wavelength is 4 times L? It's quite common in making antennas, for example, for radio waves or microwaves, that the size of the antenna is somehow comparable to or related to the wavelength of the waves being produced by that antenna. So here you have an antenna whose length is L, and you have a wave. I don't know if I can draw it, but you have a wave. You have a wave which is much longer. You have a wave in which the wavelength from here, I guess it would be from here. Well, here's the rest of the wave. No, here's one wave. Here's a second wave. So actually, I didn't draw this very well. This wavelength from here to here, or from here to here, supposedly 4 times the length of the antenna. And the question is, what's the frequency? Well, again, one of the equations that you need on your equation sheet is that wavelength times frequency is equal to speed. You know, speed is distance over time. Frequency is 1 over the period of oscillation. In one period of oscillation, one wavelength of the wave will pass by that point. And so the distance divided by the time, lambda over t, is equal to the speed. And now it's just a question to calculate the frequency. So that's another easy one. This one has to do with energies and the energy flux, or the power flux. You have an electromagnetic wave with an amplitude alpha. What's the amplitude of the magnetic field? Well, that's like a problem we just did a minute ago. E has the form alpha sine kx minus omega t times the direction of oscillation of the electric field if you want to make it a vector. Let's say it's oscillating in the x direction. Oh no, it's traveling in the x direction. So it has to be oscillating in a direction perpendicular to x. So let's say it's oscillating in the y direction. And B has to be, making this a vector, B has to be perpendicular to both E and the direction of oscillation. So that must be in the k direction, the z direction. So to make B a vector, I could say it's oscillating in the z direction. And the amplitude is alpha divided by c, and it has the same sine kx minus omega t position and time dependence. Now the energy density, which depends on x and t, will be 1/2 epsilon 0 e squared plus 1 over 2 mu 0 b squared. So that's something that depends on position and time. So if the question asks, what's the energy density? Well, there wouldn't be a simple answer. The answer would be, it depends on position and time. However, that's not what the question asks. The question asks, what's the time averaged energy density? So you want to take 1/2 epsilon 0 alpha squared sine squared plus alpha squared over 2 mu naught c squared sine squared. And then you want to average over time. You know, at any particular point, the electric field is oscillating up and down. So the electric energy between, between plus alpha and minus alpha. Okay, so the electric field is oscillating between 1/2 epsilon 0 alpha squared and 0. So it's oscillating between 0 and 1/2 epsilon 0 alpha squared. Well, the average will be 1/2 epsilon 0 alpha squared. The sine squared oscillates between 0 and 1, so the average is 1/2. So E squared average is alpha squared over 2. B squared average is alpha squared over C squared divided by 2. And 1 over C squared is mu 0 epsilon 0. Remember, that's one of the equations. The speed of light is 1 over the square root of mu 0 epsilon 0. That's one of the equations from the equation sheet, or from the exam study guide. So 1 over C squared is mu 0 epsilon 0, alpha squared over 2. Now that means if you multiply this by 1/2 epsilon 0, you get 1/4 epsilon 0 E squared. And if you multiply this by 1 over 2 mu 0, you get 1/4 epsilon 0 alpha squared. So in fact, these will both be equal. So U average will be 1/4 epsilon 0 alpha squared plus 1/4 epsilon 0 alpha squared would be epsilon 0 alpha squared over 2. So that's the average energy per unit volume at some point in the wave. You know, suppose you look at this point, around this little volume, the energy per unit volume is epsilon 0 alpha squared over 2. Now, part B is to calculate the energy flux, and you can do that using the equation from the equation sheet. It's the pointing vector is 1 over mu 0 E times B. That's the pointing vector, which is the energy flux. But that depends on time. The average energy flux, you average that over time. Well, E will have a factor sine squared. B will have a factor sine squared. The average of sine squared is 1/2. So you got 1 over 2 mu 0, E0, B0. In fact, that will just be the speed of light times the amount of energy in this little volume, or the energy per unit volume in this little volume. That's because this whole wave is moving off to the right. So all of the energy in this volume is going to pass through this area. So the power per unit area, power going through this little area, will just be the amount of energy upstream by an amount C times delta T. So that's the answer to A. The answer to B is the average of this, which will be 1 over mu 0 E max times B max times 1/2 from averaging the sine squared. So that's a property of electromagnetic waves. They carry energy in the electric field and an equal amount of energy in the magnetic field. Here's another problem involving a propagating wave. Let's say the wave consists of laser light. Now there'll be an electric field. There'll be an electric field with some maximum value. And if the value is too large, it'll cause sparking in the air. So this maximum value E max E sub max will have to be less than 3 times 10 to the 6 volts per meter for the wave to propagate through the air. Otherwise, there's sparking. Then all bets are off, because the electromagnetic waves are, Maxwell's solution in empty space, where there is no charge. Well, if you're producing sparking in the air, that's called dielectric breakdown, then that means there's charge present and things will be different. So you have to have, in order to have the equations for propagation, you have to have the electric field less than the dielectric breakdown field, 3 million volts per meter. And of course, that's a huge electric field. So you're not going to find a laser in everyday life which has anywhere near that high an energy density. But maybe in an industrial laser, some lasers are used to cut metals, and they have much higher values of electric field. So anyway, the maximum possible is sort of 3 million volts per meter. First question is, what's the corresponding magnetic field? And the second question is, what's the intensity? Those are pretty easy questions if you have the equation sheet. I mean, on the equation sheet, you have the equation, B is E over C. C is the speed of light. That's the speed of light in vacuum. Really, I suppose it should be the speed of light in air, but that's almost the same as in vacuum. So, E is 3 million volts per meter. C is 300 million meters per second. So this would be 3 over 300, 0.01, 0.01, 10 to the minus 2 volts seconds per meter squared is the same as Tesla's. So again, this would be an incredibly large magnetic field in an electromagnetic wave, maybe some industrial laser. And now what about the intensity? Well, remember from the equation sheet, intensity is energy flux averaged over time. So it's the Poynting vector, that's the energy flux, 1 over mu 0 E times B. You have to average over E times B. So E, remember, is some amplitude alpha sine kx minus omega t. B is alpha over C sine kx minus omega t. You'll have sine squared kx minus omega t. Viewed as an oscillation in time, that's oscillating between 0 and 1. So the average value is a half. So again, you'll have, the average value of sine squared is a half, because sine varies between minus 1 and 1. Sine squared varies between 0 and 1. The average value is a half. So I have here 1 over mu 0, 1 half E max times B max. E max is 3 times 10 to the 6. B max is 10 to the minus 2. So, it's going to be something like 1,000 watts per square meter. Intensity is power per unit area. So the unit of area will be square meters. The unit of power will be watts. So, I have here 10 to the 6. I have here 10 to the minus 2. So it's going to be something on the order of, well, I have to take into account the mu 0, I guess. Anyway, it's going to be a very huge power in each. Of course, needless to say, it won't be possible to create a laser beam 1 meter squared in area. It might be 1 millimeter squared, 10 to the minus 6 meters squared. It would be a very narrow beam, but that's the kind of energy that's used to cut iron with a laser beam. All right, so that one is pretty straightforward. That one's pretty easy. It just uses these simple equations from the equation sheet. And that's the kind of, well, this is a problem from the homework assignment. And you could have problems like this on the exam where you just need to know the equations. Actually, this problem is a problem in the book. in chapter 31. In fact, I think the odd number problems, the answers are in the back of the book. So you might be able to look up the answer in the back of the book because this is an odd numbered problem. But anyway, that's why you need for the exam an equation with a good, an equation sheet with a good set of equations. All right. Oh, here's a problem which has to do with radiation pressure. Radiation pressure is, well, if light hits a surface, it exerts a pressure. Now, pressure is pretty weak. I mean, the pressure of light is not very strong. The pressure of the atmosphere is 15 pounds per square inch. So on each square inch of a surface, there's a force of 15 pounds. So atmospheric pressure is quite a strong pressure. But if you had a flashlight and you shined a flashlight on a square inch of some surface, the amount of pressure would be tiny. But on an astronomical scale, it can be important. And an example of that is in comets. You have a comet which is traveling around on this line. A comet is a little piece of ice and dust which is orbiting the sun in the solar system. And here is the direction of the sun down here. The sun is down here. The comet is traveling like this, and it has a whole orbit where it comes close to the sun and it goes far away from the sun. When it comes close to the sun boils off some of the surface and then reflects. Well, that produces gas and dust. And then the sunlight will reflect from that gas and dust. And you get a very large region of light emission. Now, in fact, that's called the tail of the comet. But in fact, a comet will have two tails. It'll have a tail made of gas, which will point more or less directly away from the sun. And it'll have a tail made of dust, which will point somewhat away from the sun, but also somewhat spread out in a larger region. What causes the gas, the materials from the comet itself is a little tiny thing here. But the light is a very large thing, which comes from the materials that have been boiled off the comet by the heat of the sun. Well, anyway, what causes the material to be pushed away from the sun is not gravity. Gravity is what keeps the comet in orbit around the sun along this trail. But the gas and the dust don't follow along that orbit. They're pushed away from the sun, and what pushes them away from the sun is radiation pressure. Sunlight pushes that gas and dust away from the sun. And because the nature of the pressure on little dust particles compared to gas molecules or gas atoms, they would be, or probably gas ions, there's a much different nature of the pressure on a charged particle like a ion as opposed to a piece of dust. So you get this separation into two tails. And now we're going to do a calculation related to that. Suppose there's a spherical dust particle. It has a mass density rho. And suppose the distance to the sun is 1 astronomical unit. 1 astronomical unit is the distance from the sun to the Earth. Now calculate the radius of that little dust particle so that the force of radiation pressure is a significant fraction of the gravitational force. In other words, so that the dust particle will not follow along the trajectory of the comet, but will be blown back by the radiation pressure. The radiation pressure has to be sufficiently large. Well, let's say it's a fraction F of the gravitational force. Let's say it's 1.5% of the gravitational force. Now, the density is going to be like the density of rock, the density of a meteorite. Let's say 1960 kilograms per cubic meter. Density of water is 1,000 kilograms per cubic meter, so this is 2 times that. And now the question is, how big is this dust particle? So here's the dust particle. It has a radius r. And that's what we're trying to calculate, that radius. Now the dust particle is pulled towards the sun, so here's the sun down here, by the gravitational force. Gravitational force, according to Newton's law of gravitation, is g(m)m over d squared, where m is the mass of the sun and m is the mass of the little dust particle. And d is the distance from the dust particle to the center of the sun. That's this 1 astronomical unit. And now it's pushed in this direction. It's pushed away from the sun by the radiation pressure. And the force of any pressure is the pressure times the area. So the force due to the radiation pressure is the radiation pressure times the area, namely the cross-sectional area of this little sphere, pi r squared. I guess I also have to know what's the mass of the dust grain. Well, it's the density times the volume. The volume is 4/3 pi r cubed. So I have this equation. The pressure times pi r squared is equal to this fraction, 1.5% of the gravitational force, gm over d squared, 4/3 pi r cubed rho. And the problem is to solve for r. Everything else is given here. Well, you have to look up the mass of the sun. But you can look up the mass of the sun either in the back of the textbook or just do a Google search. You also have to know Newton's gravitational constant. Again, you can look up Newton's gravitational constant by a Google search. Density is given. The distance is 1 AU. Well, you've got to convert that into meters. So you have to know how to convert astronomical units to meters. Astronomical units is the distance from the Earth to the sun. So we're assuming that this comet comes very close to the sun, as close as the Earth's orbit. So you need to get some numbers. M is the solar mass. You can look that up by a Google search. D is 1 AU. It's approximately 150 million kilometers. I guess it's 149.6 kilometers if you do it accurately. You can find these numbers on the internet or in the back of the book. Oh, you also have to know what is the radiation pressure. Well, that's written down in the equation sheet. Remember, one of the boxes in the equation sheet was radiation pressure. It's intensity divided by the speed of light. Or since the dust grain is reflective, I mean, after all, we can see the dust tail, so it reflects the light. So the radiation pressure should be 2 times the intensity times divided by the speed of light. Now you need to know the intensity of light from the sun. Well, the intensity of light from the sun at the distance to the Earth is called the solar constant. This is the intensity of sunlight hitting the Earth. Remember, intensity is power per unit area. So the solar constant is approximately 1,400, a little closer, 1,366 watts per meter squared. So every meter squared on the Earth is absorbing an energy, 1,366 watts, 1.4 kilowatts. That's quite a lot. That's why some people think we could use solar power instead of burning coal to create electricity. So, for example, MSU has a large number of solar panels constructed on all the parking lots. Go to any of the parking lots, you'll find the parking spaces are all covered with solar panels. Well, that's because there's 1.4 kilowatts of energy available in the sunlight. Those solar panels are converting that into electric power. So some fraction of the electric power that the campus uses is solar power. Anyway, this is, again, a number that you could look up. You could do a Google search for solar constant. So now you have all the numbers here. It's just a question of getting out your calculator. You never use your calculator until you've simplified everything down by algebra, until all you have to do is plug in the numbers. But simplify this so that you get a formula for R. You see, it's very simple. Divide both sides of the equation by R squared. Divide both sides of the equation by this constant. Then you have R equals something or other where you know all the numbers, and just plug in the numbers with your calculator. Or probably a little easier, write a computer program to calculate the number. All right, so that's an example with radiation pressure. It's an example from the homework assignment. It's possible there could be a problem with radiation pressure on the exam. I don't know. I don't know what's on the exam, but anyway. The final problem on the homework assignment has to do with, again, power. It's the power of produced by a radio antenna. Suppose a radio antenna emits power P0 uniformly in all directions. So here's the antenna. And here are the electromagnetic waves going out from the antenna in all directions. And assume that it's uniform in all directions. Of course, some of the waves will come down and hit the Earth, but assume they just reflect off the Earth and they'll come up. And so where you have your receiver, maybe you have your receiver out here. So you'll have another antenna out here to receive the radio waves. It'll receive the radio waves directly from the antenna, and also any waves that hit the Earth and came up to the receiver. And you're supposed to calculate the magnitude of the pointing vector at some distance, r. So put this in a different color. Let's say this distance, oops. This distance is r. Calculate the magnitude of the pointing vector at a distance r and the strength of the electric field, the strength of the electric force on an electron. Because what happens in the receiver is that the electrons are set into oscillation. This is an electromagnetic wave, so it has an oscillating electric field. And when it hits the receiver, when it hits the antenna, which is just a metal rod, just a conducting rod, that will set the electrons into an oscillation. And then that oscillation, that current is interpreted by the radio circuit and convert it into sound. So how big a force is required? Now, let's say the power is 29 kilowatts. So I don't know, maybe this is WKAR. WKAR emitting 29 kilowatts of power. And you're 12 kilometers away, you're listening to WKAR. What's the pointing vector that your radio is picking up? And how large of electric force does that correspond? What size of electric force is that producing to create the reception? All right, so P0 is given, 29 kilowatts. The pointing vector is the power per unit area. Now, all of this area goes out into a sphere, and the area of a sphere is 4 pi r squared. So remember, the intensity, the power intensity is the pointing vector. That's the power per unit area. Now, the total power is P0, and it all spreads out into an area A at this distance r. So here's the area A, or a little section of it. Well, the area is 4 pi r squared. This is the power per unit area. So we often say that the intensity of light decreases as 1 over r squared from the source. It's the same for visible light. If you have a light bulb, what's the intensity at a distance one mile away from the light bulb? Well, the intensity goes like 1 over r squared, 1 over the distance squared. So that's the intensity. That's watts per meter squared. So part A is pretty easy. You just take 29 kilowatts divided by 4 pi times 12.3 kilometers squared. And that'll give you S. So now you have S. And now you want to know what's the electric field, because it's the electric field which is stimulating the receiving antenna. Well, remember, the pointing vector is 1 over mu 0 E times B. And B is E divided by C. So here are a couple of the equations that we had on the equation sheet. And, you know, maybe we should take the time average. Probably ought to take the time average. This should be probably the time average of the total power. So I don't know, maybe you want to divide by 2. I probably didn't divide by 2 in making up the answer to the question. So anyway, I can solve for E. If I take the time average of E squared, I get the RMS, root mean square electric field. So I really ought to take the time average of this, I guess. And so this would be the RMS, root mean square electric field squared, is the square root of mu 0 times C times S. Well, that gives me the root mean square electric field. You know, the electric field oscillates between negative alpha and positive alpha. So its average value is 0. But the root mean square average value will be alpha over the square root of 2. Because E squared is alpha squared, sine squared omega t. The average of sine squared is a half. So E squared RMS will be 1/2 the amplitude squared. And then what the question asks is, what's the force? How big is the force? And that's the electric charge of the particle, namely the electron, times the electric field, because that's the electric force. It's charge times field in the case of the electric field. So again, this is a problem where you have to use those equations that we had from the exam study guide. And then put those equations together before you start plugging in the numbers. Once you've got the final formula for the force in algebraic form, just put the numbers into your calculator. This is again a problem from the book. This is a problem in chapter 31. So actually, I think the answers to the odd number problems are in the back of the book. So since this is an odd number problem, the answer might be in the back of the book. I'm not sure. You can expect this to be a very small force because after all, we're just talking about the force on an electron. The electron is a very small mass. So it doesn't take a very strong force to cause oscillations of such a small mass. So this will be, you know, many powers of 10 smaller than a Newton. So you should expect your answer to come out to be, you know, some very small power of 10. Well, okay, so those are the problems I was prepared to discuss tonight. We're almost at 8 o'clock. Before I stop the video, are there any questions?
I do have a question. So yeah. I couldn't go on Professor Nagy's website. Like the web page wasn't working for me.
Oh, there is a web page where he has hints for the problems.
Yeah, I could not.
Talking about?
Yes, that is what I'm talking about. Yeah.
Now, I've always been able to reach that web page.
I couldn't access it today.
You might try again, and if you still can't reach it, you might send him an email.
I think other people in the class were also having the same issue.
Oh, okay. Well, hopefully he got an email from somebody that says there's. I don't know that he really is in control of that website. I think that's a website that belongs to the physics department, and he may not be able to control it, but he should be able to, well, he should be able to talk to somebody who's in control of that. Maybe he just didn't see his email. It should, I'll send him a message that I'll also send him a message to see if he can get it. The homework's due Thursday. So you still have 48 hours to do the homework, and you will need, you know, I think it's good to use those hints that are on his website. So I'll send him a message to say, check your website and see if you can get it started again.
Is there any way you could like email the hints to everyone or have them available?
I don't think he has them in that form. I think he has them in the form of web. You know, you have to look it up on the web. As far as I know, that's the only way that's the only way to get access to it.
All right, thank you.
Yeah. Any other last minute questions? I'm going to stop the share. Stop the recording, I guess. Let's see. I have to stop the recording.